Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great honor and pleasure to introduce Gennady Kasparov, who will deliver a lecture, Orbital and Transverse Index Theory for a Lie group action. Gennady, the Zoom is yours, the floor is yours, take it away.
Okay, let me first thank the organizers for inviting me to give a talk. And I start by saying, well, I want to say that I will take the a little bit easier case of compact Lie group action, although everything generalizes perfectly to the proper Lie group action on a complete Riemannian manifold. The necessary changes if I see something which well, whatever in the process there is something which has to be changed for the proper Lie group case, I will try to indicate. First, I want to make a small review of the procedure which I call coarse construction of pseudo-differential operators. And this it's not something different from Hermander's definition of pseudo-differential operators, which is commonly used right now. It's simply just a certain simplification, eliminating infinite number of derivatives and leaving maybe just one derivative necessary for the symbol, because the whole process of constructing an operator is already complicated stuff in Hermander's setting, and so it's in the proofs to prove certain things becomes quite boring. So we take a compact space, and D will be a C-star algebra, and the C of x, continuous functions on x, and with representations in multipliers of D, a unital homomorphism, and given a bounded non-continuous function, operator function, with values in multipliers, which commutes with the image of this homomorphism modulo D, which essentially D will be assumed to be compact operators later. Compact or whatever you want, which serves as compact operators. Then there exists an integral which defined as a Riemann integral, almost the same definition. So let me explain the definition.
May I have a question? Sorry.
Hello? Sorry?
Can I have a question?
Go ahead, Tom.
I don't hear me.
Go ahead, Tom.
I hear very.
Are you using this notation with this like measure-like element d phi for a purpose? Are you relating this integration with only with this phi map?
It's completely abstract. I haven't said anything about operator.
This phi has anything to do with this phi, which is the notation for this map from C of x to multiplier of B.
Yeah, look, here I have a map, right, phi, and here you have d phi. So Tomek asks if it's a coincidence.
Yes, it's it's a continuous. Yes, it's a homomorphism. Yes.
So in a sense, your phi is, in a sense, is a limit of atomic measures, something like this. You have nodes, like in the Riemann integral, you have nodes.
It's used as a measure, yes. If you want
Riemann
it,
sum.
it's used as a measure, yes.
Okay, I see. Thank you.
But it's a multiplicative measure. The measure is multiplicative. Not only positive because it's homomorphism of sister algebras, but it's also multiplicative, and alpha i's are positive partition of unity. So I take this positive partition of unity associated with the finite covering, and the integral will be just defined as a limit of these integral sums. Of course, it's necessary to prove that it converges, but I don't want to spend time for this. It's just a certain exercise. So what I might have missed to saying something. Well, I cannot. It's interesting. I cannot move. So the whole thing, if you want, is in this article, all details. So if you want all details on this course or this operator integral, actually the integral is known from the 70s when I first wrote my first article on index theory. But this requires a little bit of the adaptation for the case of non-compact X. Not very essential. Okay, so let's go on. This operator integral is important that it's multiplicative. Not only additive but multiplicative because the measure is multiplicative. It preserves joints, and it's bounded if the function is bounded by the same constant. All modular compact operators, of course, because the definition is given by modular compact operators. I forgot to write here that it's modular compact operators, but it's all estimates are modular compact operators. So now, how this can be used to construct differential operators? We take a compact manifold, and T of X will be its tangent bundle. The total space of the tangent bundle is Tx, projection P, and we'll use Riemannian metric on the manifolds, on the bundles, on everything. So this will play a very important role. So the whole definition will be metric definition in a sense. Now the operators which we'll construct will be order 0 operators. It doesn't allow to construct differential operators or something like that, nor the negative order particular parametrices. But of course, if you need to deal with differential operators or some parametrices, you can always shift to Harmonic calculus, which is completely compatible with this coarse calculus. The coarse calculus is only good for order 0 and negative order operators. Essentially, the whole index theory is designed this way. You have the index of 0 order operators modulo negative order operators. That's what you have. Now the symbol of operator F will be denoted by sigma F, and this operator will act on a section of certain vector bundles, which usually I will denote by E. Now the we consider
Question about your notation, since before f was denoting the function, so you somehow identified the.
Oh yes, I'm sorry. The notation. I tried to be consistent with notation, but in this case, it's it's a lapse. You are right. F. This F is not a good thing to. Well, you may use any other letter. It's I agree with you. It's not that F and this F are different.
Another F. Okay. Okay. Thank
you. So it's the symbol should be a bounded operator on the lifted bundle. The bundle lifted to the total space Tx, and I think these headphones don't help me at all. I probably don't work. So the symbol should be norm continuous, which means that working in Hermander class, I should choose rho equal to 1, delta equal to 0. But it's not a big deal, because in current say hyperelliptic setting, it's quite usual thing to do. Well, essentially, I am thinking already quite some time to rewrite the whole construction to hyperelliptic setting. Now, the important so this condition, first condition, requires actually some trivialization of the tangent bundle. But the second condition is designed not only to make symbol vanishing in xi at infinity, the derivative of xi in xi at infinity, but also the two conditions are invariant for any continuous change of coordinates in the tangent bundle. It's a lemma which I will not prove, but it's certainly contained in the paper. So the two conditions mean that it's a reasonable set of symbols, and it doesn't require infinite number of derivatives at all, with just one. Now, the co-symbol is the Fourier transform in xi. For any x, we can, well, essentially, what is a pseudo-differential operator? If you take a pseudo-differential operator on the Euclidean space, which has constant symbol, constant in x, you just take a Fourier transform xi. You transform. You take the map of Fourier transform, then you apply your symbol, and then you take Fourier transform back. That's what is written here. You take phi, then sigma, then phi inverse. The co-symbol, due to this second assumption, commutes with multiplication by continuous functions on this L2. I mean, if you multiply by any continuous function on L2 of x, it will continue, it will commute up to compact operators. So that's the condition that we need. And now the way to define the operator with the given co-symbol is to take a finite covering of x by so small Riemannian balls that if you take the corresponding Euclidean balls, which correspond to these balls via the exponential map. The exponential map gives you the correspondence between this Euclidean ball and the remaining bold UI. In VI, at this tangent space, you have the co-symbol. And in order to make sure that you can use it locally, you have to cut it by some cutting function. It's not important exactly which function you take, modulo compact operators, any function which is any continuous function which is equal to 1 at the center of the ball gives the same operator, modulo compact operators. So that's another lemma which is also easy to prove. It's very much similar to Hermander thing that singular support is on the diagonal, and we transplant this operator into this space L2 restricted to the neighborhood UI, open set UI. And this gives the operator already on the whole set because it acts on the subspace. This is the subspace of this space. Now, taking a partition of unity, you can write an integral as before and pass to the limit and get an operator. So that's of course one needs to check all conditions that everything is converges, but it's kind of routine thing, and so you get essentially almost for free your pseudo-differential operator out of the symbol without much Fourier integrals, just almost for nothing, at no price. So the whole thing is defined modulo compact operators, and the correspondence between the symbol and the operator enjoys all properties that you want to have: the additivity, multiplicativity, stability by the conjugation, passing to the adjoints, preserved boundedness, all modulo compact operators. And the resulting operator is the same. If you started with Hermander rho equal to 1 delta 0 class operator, so all your family of symbols satisfies this condition, then it's easy to prove that modulo compact operators you get still the operator modulo compact operators the same as Hermander's operator. So that's a good answer to this problem of constructing. Now, so this procedure was used consistently in this research and simplified quite a lot of points, and definitions as well, because definitions don't require many derivatives at all. But let's go now to the main topic. So we assume that a compact Lie group acts on a compact manifold, and we fix Riemannian matrix, which will always play a role. The Riemannian matrix on G and X, and the action should be isometric. Now, the Lie algebra will be denoted by Gothic G, and we'll use some sometimes short notation Please note this for tangent space because it's quite complicated in the cell phone.
So probably this F should go into X cross X, yes? This G action. Yes?
Yes,
Okay.
yes, you are right. Yes, it is an error. Yes, but essentially I will use mainly well. Yes, I wrote this because when we construct operators, we will construct them on this space rather than X cross X, and it will be pushed like forward. Yes, you are right. I had to write actually. So the part which maps G into G of X will be called Fx. This Fx it maps G into X at any point X. Now, what is important is the tangent map. The tangent map, first derivative map, and we'll consider also the trivial bundle X cross G with the G action given by this formula. It's easy to show that this map F prime is G equivalent. This map is G equivalent. Well, now we can choose the G invariant remaining matrix on this vector bundle using the fact that the G action is proper. Well, the G action I forgot to when I was writing the slide, I already forgot that the group is compact. But anyway, in the proper group action case, it's still possible. So we can normalize this remaining matrix such that this condition is satisfied just by multiplying this by some positive function. And this is useful to have some estimate on this derivative everywhere. Now we will identify T with T star and Gx with G star X using the Riemannian matrix and consider the adjoint maps, which is important to have. This adjoint map will play this map F of star plays an important role, and just note this notation phi x. Y square root, it's well, it's essentially because of this formula. We define the quadratic form by the square, the norm square of this vector, covector, and it appears that this square is equal to that square as well. So that's a good definition in this sense. It will be used. So our assumption essentially tells us that this form satisfies this condition. But not only this, this form actually is very well adapted to the topology of the orbits. When the orbit collapses to, say, to one point, this form also goes to zero. This form reflects the geometry of the orbits, and so if we want a Riemannian metric on the orbit, we can choose this form for each orbit passing from through X. Of course, this form is G invariant, so it doesn't matter which X on the orbit we take. Now, okay, so now we come to the orbit. Well, the important thing is that one needs a kind of operators of negative order. It's an important algebra. It's everywhere in harmonic calculus or whatever other PD calculus. The zero order operators are multipliers of a certain algebra, and this is the algebra which will be used to have to serve as algebra where the actual symbols will be multipliers on. To define such algebra of negative order symbols for leafwise operators, we take the total space of this trivial bundle with the fiber G, the Lie algebra, and on this fiber bundle, so we take just X cross G, and Tx will be the total space of the tangent bundle. The pointwise map F star X of the tangent space to X to Gx induces the map on the functions in the opposite direction. So each function vanishing in infinity goes into some bounded function. And globally, we get the map of these functions which vanish at infinity fiberwise and the infinity of the X as well to bounded function on Tx. The image will be called this leafwise orbital symbols algebra, leafwise orbital symbol, SLF of X. Now, I should note that the functions in the image of this map are constant in the directions orthogonal to the orbit passing through X, which means they are not functions which vanish at infinity of X at all. They are some bounded functions on X. Okay, I can define it also in a different way. We can pass to the co-symbols if you want. So we can take a Fourier dual thing, the Fourier dual of this algebra. If you take Fourier dual for each fiber, C0 of Gx will be C star of Gx. So if you take the field of the algebra C star of Gx and take sections vanishing at infinity in X, you will get the algebra which is isomorphic by Fourier transform to this algebra. And maybe it's even more natural to take the map of this algebra into the map of this algebra into C star of Tx by using just F prime. So you take F prime X at any point. You might take the L1 functions or measures on Gx and push them to Tx, and the result will be the map of C star of Gx into C star of Tx. Not C star of Tx actually, but multipliers of C star of Tx. It's not functions which vanish at infinity. So these two maps are Fourier dual, and this will be the algebra of negative order symbols. Now, the important remark is that this element in each fiber of the algebra. So this is a subalgebra of the algebra of bounded functions on Tx. In each for each x, this function is a strictly positive element in this subalgebra. Because this element actually comes from the strictly positive element in the C0 in the I should probably have written here some other letter, not psi but eta. In the Lie algebra, if you take 1 plus eta square, the normal eta square, and you map, take the map f prime star, you will get f prime star here. F prime star norm f square of f prime star gives you exactly this form qx of xi. So this is an important fact which you have to somehow remember. It will be used. Now, for transverse symbols, the definition of transversely if you want transverse negative operators, essentially was given by Atiyah. He considered the subspace of this space, the subspace which consists of covectors orthogonal to the orbits, and he called it Tg of x. So the symbol which is invertible on Tg of x was considered by Atiyah as transversal elliptic. No restrictions on the tangent to the orbits directions. So this certain sense distinguishes the negative order symbols transverse symbols. They should satisfy the condition that the restriction of Tg of x should belong to C0 of Tg of x. C0 means vanishing at infinity. But I will use a different definition, which is equivalent. The equivalence was proved in my paper of 2016 in the Noncommutative Geometry Journal. So I will use the following definition. So the symbol algebra consists of is a subalgebra of also bounded functions. Symbols are continuous in X uniformly in Xi, which is the usual condition. Differentiable with this estimate as usual again. And third condition is that this element is a strictly positive element for this algebra. Strictly positive element for the transverse, for the algebra of transverse symbols of negative order. That's so the why it is equal, why it is equivalent. I can only explain that if you have in one direction, it's obvious. If the symbol vanishes, at infinity on the TGX, then this thing will go to 0 at infinity. So in principle, it's to a certain extent gives you some idea, but in the opposite direction, it's not quite that obvious. It requires some argument.
Sorry, may I have a question?
Yes.
In the point number 2, what does it mean P? Depends on
B, I wrote where I wrote B somewhere. I was correcting this. Yeah, I'm sorry. It's not B. It's sigma. I was correcting it from other article, and I had to look.
If you bend B a little bit, it will become a sigma.
It's sigma. It should be sigma. Yes. Yes, thank you. It's well, it's it's difficult to take different sources and put them into one. Okay, so the from the condition 3 and the previous condition on the strictly positive element for orbital algebra, we can see that this element is strictly positive for orbital operators, and the other element is strictly positive for transverse. It means that the product, which is this one, since it belongs to C0 of Tx, it's strictly positive element in C0 of Tx. It means that the product of both algebras are subalgebras of bounded functions on Tx. So the product is actually equal to C0 of Tx. And this gives a very good pairing between leafwise and transverse operators. This is the product. You see, both are modulus over C0 of X. This product of they are called C of X algebras. The product is taken pointwise over X. So this product gives an element of C0 of Tx. That's an important observation which is used.
Sorry, I have a question.
Yes, sure.
To this tensor product. So since you are balancing this tensor product over the non-unital algebra, then you don't have relations like y the first factor times the second one is equal to the first one times the second one, twice the second one. Okay? Because,
yes.
Yes, so this tensor product has strange properties, which
you have to consider both algebras as a field of as a continuous field of sister algebras over X. One LF is a continuous field of algebras with the strictly positive elements. This one and this second is a continuous field of sister algebras with this strictly positive element. When the tensor product for C of X algebras is defined. I mean, this is the case where sometimes this product is not uniquely defined in most complicated cases, but in this case everything is type 1. I don't know, very nuclear at least. So it's one field is multiple tensored with another field pointwise. This tensor product means pointwise tensor product. The pointwise fiber of one is tensored with pointwise fiber of the second one, corresponding point. So it means that for each point you get a function of x vanishing at infinity. It's exactly what is written here. You get,
but still x is compact, so there is not a problem here. X is compact. Am I right?
Yes, X is compact, yes.
So this is C of x. So there is no. So this difficulty only appears when x is non-compact. So
Yes, you're right. This is C0 of X is a bit puzzling. Gennady, I thought you assumed that X is compact manifold.
it's not. No, it's well. It's completely well. C0. I had to write C. In some places I forgot. I was forgetting to delete the 0. But in any case, if X is locally compact, it's still true. There's no problem. It's true both in compact and locally compact cases. There is no problem with this. I'm sorry. I just in some places I was making certain lapses, but it's a long thing which I was redoing from different articles. Okay. Finally, the important thing to know from technical point of view is the definition of Clifford algebra along the fibers. Well, actually, both algebras. If you consider a full algebra, if you consider Clifford algebra of the whole manifold, if you take tangent space and Q will be just usual Riemannian metric, then pointwise you have a Clifford algebra, and considering sections vanishing at infinity, you get Clifford algebra, Clifford sister algebra, which I call Cliff tau of X. If you consider only tangent vectors to the orbits, so you consider only vectors of this kind, and you take the quadratic form Qx, then you get another algebra which contains only Clifford variables in the tangent directions to the x. But it's very important algebra and will be used several times in what I'm talking about. Okay, so okay, so let me go a little bit faster, because I think I'm a little bit already past. Now I make a few reminders. If someone knows what is KK theory, you can skip this the couple of pages. So here is a certain definition for those who are unfamiliar with K theory, and an important thing here is a reminder that this is the condition which is used for KK triples. The KK triple is the Hilbert model, the homomorphism, and the operator. Now, there is an associative product, and the K theory itself is also part of KK theory, and K homology is also part of KK theory. So that's just to remind you, to kind of to give some insight to those who are not familiar with K theory. sometimes confusing is when you have to take a product like this. And to do this, you need to add 10C in the first KK here. It will be B 10D 10C, and add B in the argument here. So you get B times D times C. So you'll be able to take the product. Adding this, of course, you will add B also to E, not only the first place, but the second place, both arguments. And here also D is, and C will be added to both arguments. And then you take the product. It's a completely legitimate and simple operation. Now, what I called C of X algebra is an algebra where there's a unital homomorphism from C of X to the center of M of A. In the case of locally compact space, it's not unital. And the condition of unitality is replaced by saying that A times C of X is dense in C of X. A times if you multiply A by C of X, C0 of X, if you multiply A by C0 of X, you will get element, it will be dense in A.
Sorry, just a quick question. You mean any unital homomorphism or maybe injective?
No injectivity, no, any, yeah. But all operations which you do with C of X algebras should respect. I mean, the injectivity. I mean, the fact that A times C of X is dense in A already is a very strong condition. It's a condition that any element of A is approximable by some multiple of C of X. So C of X acts well. Essentially, what we need in all this in all that follows is any C of X algebra defines something like a field of continuous field of C-star algebras. In this case, it's not. In general, it's not quite a continuous field, but we don't need much more than sections of continuous field of C-star algebras. All examples there will be of this kind. So it's just a general definition, but in principle, you can when C of X algebras are used, you can assume that these are just sections of field of continuous field of C of X of C-star algebras over X.
And sorry, just a fixed terminology. If you have a C of X algebra, you mean that this unital homomorphism is already chosen, yes?
Yes.
Okay.
Sure. Yeah. So the RKK groups are KK groups which respect this structure of C of X model, if you want. So all algebras are C of X models. C of X structure gives a model structure, if you want. And in this definition, the homomorphism phi, which is used to define KK, should commute with the C of X section. That's so that's the point to define RKK. And the way that compact case differs from locally compact, actually, in the compact case, you have this isomorphism, which is quite obvious, actually. If you take a definition, it's quite obvious. In the locally compact case, there is no such isomorphism. And I tell you why, because this group can also be defined as operators of this t square minus 1 are compact operators. But there is no condition that phi of a times t square minus 1 are compact. This will be absent. And if X is compact, then there is a unit. So this still be the same. A unit times t square minus 1 is t square minus 1. If there is no unit, and this is C0 of X, it means that multiplying by C0 of X, t square minus 1 will be compact. Compact also means that your, for C of X algebras, it means that the norm of your operator goes to 0 if it is a field or whatever, goes to 0 when you go to infinity. So in this case, t square minus 1 is not required to go to 0, because you multiply by something which already goes to infinity. It goes to 0. You have t square minus 1 compact pointwise and bounded. You multiply by something going to 0, and you get the condition satisfied. In the right hand side, you don't have this a which phi of a which goes to 0. So the important point is that t square minus 1 should go to 0 at infinity. So here this is not required. Here it is required. So that's the difference. So you in the locally compact case, you have to keep this notation throughout. In the compact case, you may just skip certain letters quite a bit and take a shorter notation. That's now a small remark that these two algebras are KK equivalent. From KK theory point of view, they are KK equivalent. So you in any statement you can replace one of them with the other. It means that there is an invertible element in KK, in RKK, which relating these two algebras. Now let's go to the first theorem. The first theorem is what I call Poincare duality. It relates K-homology of A with this RKK of A C0 of Tx. If A is C of X, it means that K-homology of C of X is and X is compact. Then you can drop the C of X because of this condition, because of this 7, and you get K theory of T0 of X. This is what is called usually Poincare duality for compact manifolds. In general, it's still useful, but it's written in this way a little bit more complicated. And as I say, well, even in the compact case, you cannot eliminate this A because it's necessary for different applications. A is a C of X algebra. It can be, for example, Cliff gamma of X or something like that. Okay, so now we come to important thing, KK duality, RKK duality, and this means that you can well, RKK duality means that in a group like this, for arbitrary COX algebras A and B, you can shift D1, replace it with D2 by putting D2 in the second argument. So D1 is in first argument, you put it in the second. If D2 is in the first argument, you can put D1 in the second. Both isomorphisms should be true. And you do it, there should exist two elements, alpha and beta, and the whole thing is the procedure is taking the product, two products, either with one of them or the other one. So these two elements should give the isomorphisms. That's the definition of RKK duality. The combination of Poincare duality and RKK duality gives a small fact which it's very easy to prove in combining the two things. If these algebras are RKK dual, you can re-express K homology of D1 by K theory of D2 tensor C0 of Tx, like this. Okay, so first really non-trivial fact is that these two algebras are RKK dual, and moreover this algebra is RKK equivalent to C of X. This is this requires about 1.5 pages of proof, so I will not go into any. Don't have time to go into details. What I can just say that these elements alpha and beta, they are some canonical actually elements. They are not from nowhere. You take as this beta the element which uses this leaf-wise element phi x of xi, normalized to have square equal to square minus 1 to be compact in a sense. And it.
So, Tom, did you just raise a hand to ask a question?
Yes.
Yes.
My question is, could you remind me what gamma stands for? What does gamma stand for?
Gamma means leaf-wise or orbit-wise directions. Gamma, it's what I defined several slides before. You take the Clifford algebras in the orbit-wise directions, and the quadratic form is qx of xi, qx on the orbit. Then Cliff gamma gives you the algebra associated with this form.
Thank you.
You take only orbit-wise or tangent to orbit directions or vectors. And this is a leaf-wise negative order operators. Okay, so the element alpha is also not quite trivial, and it lives actually, I would say, in infinite dimensions. You cannot. I couldn't construct it in. So it's constructed on a field parameterized by x, but the parameter the algebra is something like compact operators on L2 of lambda is means exterior power of the tangent bundle. This is a Dirac operator. This operator of index 1, but it doesn't commute well with this algebra, because all Clifford variables already used, and this algebra needs some more Clifford variables. However, we have the algebra which kills the commutators which are just not good enough. So this algebra kills some. This is also a leafwise algebra. It kills some commutators. Well, to explain more details, I just wanted to show this because these results come from not from nowhere, but they have some background. Okay. And finally, the result which we need is a certain theorem which says that which associates to the transverse algebra, transverse operator algebra of transverse symbols. This algebra, there is a certain algebra which is more treatable and easy to deal with, and it appears that they are RKK equivalent, which means that there is an invertible element joining them. The only problem is that one needs some techniques not very complicated, how to deal with non-separable algebras when they appear in the first argument of the KK theory, because product is usually defined for algebras where in the first argument there is a separable algebra. If non-separable, then one should have some additional tools. But it doesn't affect much the proof. But in any case, I just mentioned this because it requires some to state the statement requires some caution. But it also proof of some I don't know, page and a half maybe. So now the corollary which I wanted to show you is this for compact space. This is only for compact space. For non-compact, the whole thing should be ornamented by some RKKs. It also exists in local compact case, but in the compact cases is pretty simple. The K theory of the transverse algebra, the transverse symbol algebra, and the K homology of leafwise algebra are isomorphic, and so essentially the duality between these two algebras extend to equality of K theory and K homology. And the proof is pretty simple. You say in the first case you start with K homology, you apply Poincare duality, and you get this thing.
Someone gave a question. Just ask a question. Why?
Yes, I have a question. Yes.
Yeah.
When you started speaking that if S trace is this transversal is not separate, could you explain shortly what's the reason of this non-separability, even if the action of G is proper or G is compact? What is the source of this algebra being not separable?
Non-separable.
Yeah.
Well, yeah, because the only thing is the only thing we know is that there is a strictly positive element. There is no indication that there is a you see, the algebra of bounded functions is non-separable. Now you take a separable algebra, which is this one, the leafwise is separable as an image of a separable algebra, and you take essentially the annihilator of this algebra in the or annihilator, I mean modulo C0 of Tx. You take some algebra which is maps bounded operators into which map, well, this algebra maps separable algebra into separable algebra. There is no other condition. You can you multiply in the non-separable algebra, you take all elements which move a certain separable subalgebra into separable subalgebra. You have no other condition which distinguishes this S tier. I don't see any way to prove that it's separable.
I don't understand why this is not separable. So if X is compact,
Yeah.
then symbols can be non-separable because of non-compactness in the tangent directions. And this, am I right? Is it the source of not being separable for this algebra transversal symbols?
No, I don't think it's a very obstacle to anything. It's just it doesn't make more difficult to deal with this. I don't see any trouble in non-separability.
Thank you.
Okay, so this argument is pretty simple, and you use just k-duality, and then you use this last theorem, and then you get the result. And the second isomorphism is pretty similar. So this is kind of nice statement that the two algebras are, in a sense, completely dual. And we can also specify precisely the pairing between the two things, and it is quite natural. You have the product of two these things sitting in C0 of Tx. In K theory of this is isomorphic to K homology of C of X by Poincare duality, and then this group, if X is compact, then it restricts to constant functions and to R, which is R of G, gives K theory of 1 point. If X is non-compact, then the last arrow is not possible. You stay in K star G of C0 of X. Okay, now the construction of leafwise PDOs is I spent quite some time on this because it's the structure of the orbit space may be very complicated, so one needs to approach it in a good way. Well, first of all, I want to say that the construction will be given more or less. I will explain how it is done. But it can be done in two different settings. G equivariant symbols lead to G equivariant operators, and there is also a possibility to take stabilizer invariant symbols. It means that stabilizer invariant, well, essentially it means that for any point, the symbol is invariant with respect to stability subgroup, but at least a little bit more complicated, actually. You need invariance on the tubular neighborhood of every orbit, and invariance under the stability subgroup for the tubular neighborhood of the restriction to the tubular neighborhood. Well, vector bundles we call E, and the Hill model will also be called E, just not to change notation much. Now we have the map, which is essentially given by map C0 of Sx to SLX, SLF of X. So this map is surjective, so it extends to multipliers. And what we do that we call we define a symbol as an element which comes from here, from this space, actually. So our sigma, which will be here, comes as an image of something from here. So this B of X eta should satisfy continuity, non-continuity, and differentiability as usual. But of course, if we map it onto the orbit space onto X, it may not be so good, so nice. For example, if you take just an operator like d plus d star on the manifold, well, you normalize it towards 0. On each orbit, on each G, group G passing through, I mean, well, essentially that's exactly what I meant by adding this G cross X, G times X map F into X times X on G times X. This thing is just constant. It has the same symbol at every point. D plus D star is just some Clifford multiplication. But when you map it to the orbit, it will vary. It will not be so nice. It will have some singularities and so on. So we start with something which was very good, and then then after we do some preliminary construction on the group itself, on the group, then we will map it to the orbit. So for that reason, we take this maybe called pre-symbol, and then the symbol itself is a kind of the image of this B. Now the symbol is called negative order if it belongs to the compact operators on this algebra. Now to construct the operator, we just take the covering by tubular neighborhoods of the orbits. We construct this and there is a small result which says that we want to see the operator to be in the sister algebra. We want the operator to be in this sister algebra of where it is written. Okay, we want the symbol to be in sister G, comma K of E. So when we restrict it to each UX, each tubular neighborhood, it becomes this. It's not very difficult to prove. Then we construct the operator on L2 of G, and after that we glue everything together using partition of unity. So that's essentially, I think that's what is written here. So on L2 we can always construct an operator, and then the final element in C star of G, comma K of E comes as a result of we sum up all these operators. Now the construction, of course, on L2 of G is a standard, uses this standard coarse PDO construction, which I mentioned at the beginning. So it doesn't even require this strong estimate on the derivative, that the derivative decays like 1 plus xi inverse. It requires only decay at infinity, and that's it, because there is no change of variables. G is has a canonical system of coordinates.
So, sorry, Tomek, if you have a question, just ask it. Don't raise hand.
Okay.
Yeah.
So my question is whether this construction is independent of the choice of local slices.
The choice of what?
You are using the slice theorem. So I suppose this construction is independent of the choice of the slice. Is it so?
The choice of this covering by UX.
Yeah. So you are using the slice theorem here.
It's It's
not me.
yes, this you mean the isomorphism using different presentations of the yes, it requires some proof that it doesn't depend on the
Oh, I expect it. Thank you very much.
Yeah, well, it's about the same as the proof that construction of pseudo-differential operator doesn't depend on the covering of the manifold by open sets which are small enough. So it's of the same. It's of the same kind of
Yeah,
state.
I want to be sure. Thank you.
So essentially, what we get after all, we get an operator in this algebra, a multiplier of this algebra, using this construction. And the important thing is that if the symbol was negative order, which means that it was vanishing at infinity. Well, negative order means when you multiply by let me see, negative order if it belongs to this compact operators of compact operators of this kind. Then the result will be in this algebra C star of G KV. So this is like compact operator subalgebra, which model which everything all this calculus works. Now what we need is that the orbital operators like Dirac type operators, Euler characteristic operators. We can define them using the usual formulas and then normalize. The point is at every in every construction, in that construction as well, one needs to push everything to the manifold after it is constructed on L2 of G or using the slices or whatever. Everything is pushed on the manifold. On each orbit, you may have certain construction, but then you push it to the manifold, and on the manifold, on the orbit, you get a final operator. And the same thing happens also here. The operator, the symbol here for the operator for the Euler characteristic, for example, is this one. Clifford multiplication means x plus int. When you push it, you get Clifford multiplication by this covector, and instead of eta square, you get this one. So this is the okay. I'm quite behind already. In the index theory, the usual assumptions are either you look at self-adjoint graded or non-graded, and depending on this, you get either K0 or K0, K1. And the definition of the elliptic operators is absolutely standard, the same in all cases. Of course, in the locally compact case, you need to add here a function from Z0 of x. C0 of x times sigma square minus 1 belongs to compact operators. In the compact case, you don't need this C0 of x. But this standard definition of the index. Now so to summarize for compact case, the orbital Clifford algebra, orbital elliptic symbol groups are these ones. Orbital index groups are these ones, and this is, by the way, isomorphic to this group. in the compact case again. In the non-compact, it's more complicated. For T-elliptic, it will be this one. It's K theory of the S trace, and the T-elliptic index is in K homology of the cross product algebra. Oh, that's again, I forgot C star. So K star of C star G of C of X. This is C star. No, so many errors. Sorry about that. Now, there is a certain element which I probably will not go into details because the time is very limited. So there is a certain element which serves as the index element, like Delbo element, like whatever, to get the index for the orbital case. And this element lives in a certain group which is quite complicated in the non-compact case. I would leave X out here, and will be KKG of the leafwise algebra and comma C star of G C of X. The definition I probably will drop explaining. So there is a certain element of this kind, leafwise operator, important operator here. And the orbital index theorem is this one. You take the K theory of you take the symbol element lives here. You take a product over this algebra with this orbital Dirac, which, by the way, is constructed using the earlier characteristic operator on the lambda star X. And but using some infinite dimensional stuff also. And you take the product with this element and you get the symbol, the index. So the index is the product of the symbol with this orbital Dirac. Now, for T-elliptic, I need actually a couple of elements, but I probably will skip this again because time is very limited. So the symbol of the T-elliptic element lives in the K theory of this algebra. In K theory of this algebra. But there is a certain element which relates this algebra and this product, which I call Cliff gamma of Tx. So this tensor product. So first we map the symbol into this K theory. Into this K theory of this algebra. And then there is a Dirac Delbo element in the C star, in the K homology of C star G of the same algebra of Cliff gamma of Tx. In this group. Now, how we get the index formula, we take the homomorphism which maps equivalent groups into the K groups of cross products. So we apply this to the KK groups of cross products and take a product over C star of G, this Cliff gamma with this element. and this will be the index. The index will be it's a distributional index. I forgot to write it down. It's in K homology of C star G in the compact group case. In the compact group case, it's a C star G in the K homology of C star G. So it's infinite series in irreducible representation of G. For comparison, I gave here the statement of the usual elliptic index theorem. Now there are. Can I take 5 more minutes?
Yeah, 5 more minutes is perfectly fine. Yes, please do.
Okay, so I wanted to give a couple of examples of this stuff. And the first thing I wanted to say that the Atiyeh-Singer family index theorem is a corollary of the leafwise index theorem, because you take the quotient, you take the free action of the group on you take G space X with the free action of G, and you map you consider the family of operators on the leaves of this space over on the orbits, if you want, and this on each orbit you have an elliptic operator, and so it gives you a family of orbit-wise operators, and the result is of the indexes lives in this group. Now, more interesting example is say for example this one. You can you can take the group. It's not extremely interesting, but in any case, when you take very interesting examples, you have to take multidimensional Lie group acting on some multidimensional space. The orbit structure will be pretty complicated, and I didn't want to make calculations in complicated case. So I just wanted to show that the index is non-zero. So the space is very simple, and I take rotations, usual rotations over the axis passing from north to south pole. The S2 is considered as a one-dimensional projective space. The bundle is exterior power of tangent bundle of this manifold, and the operator is Euler characteristic operator. So to calculate the whole thing, I take just the index in 2 points in 2 poles. They are fixed points, and the rest of the action is free. So in 2 points. So the exact sequence gives the embedding of this K0 of C of X into K0 of C plus C, and the index is actually comes from C plus C. It's just so this group is representation ring plus 1 minus rho representation ring. Rho is the basic representation of the S1, and
I have a question.
Yeah.
You wrote on the previous page, you wrote this, that lambda star of CP1 is a complex line bundle, which means that
No, it's no, not lambda. The tangent bundle is line lambda star. Sorry.
okay, so
The tangent the tangent bundle of CP1 is line bundle.
yeah.
Yeah, it's no, lambda star is exterior bound.
Complex vector bundle.
Yeah, it's sorry, too many errors. So the maps are model maps, and the index is functorial. The calculation of the index at the poles is very simple because the poles are fixed points. It's plus minus 1 minus rho. So the whole index is just this one. Now a T as example of T elliptic operator is much more sophisticated because it's pretty strange that such thing can be transversal elliptic, but it is. This operator is converted into self-adjoint in the usual way, and then divided by something which normalizes this to order 0. So it essentially compactifies the complex the C1 into the two-dimensional sphere. So this puts our the whole thing in the compact situation, and we can calculate the index, which is distributional index. The analytical part is very simple and well known, and it gives the sum of representations which are powers of the basic representation, all powers from 0 to infinity. But more interesting is to calculate the topological index, how the index theorem works, and the index theorem works in this way. One can tensor the whole thing by extra copy of this bundle, and then when we tensor by this, we can make a homotopy of the differential operator to the elliptic one. So this we just multiply this differential part. No, excuse me, not differential part. We multiply by multiplication part. Differential part is fixed and doesn't change. We change the multiplication part. We multiply it by cosine and the sine. So we make a rotation, a certain rotation of the multiplication part. And when t is equal pi over 2, then we get the operator which is elliptic, because this part and this part, they anticommute in the gradient sense. And so what happens is that we get elliptic symbol, and this is elliptic symbol. It has index 1 in R of G, and this the Z2 gradient representation with which we tensored has the form 1 minus rho in the representation ring. So we have to divide by this back to get the symbol of the to get the index of the initial operator. So the multiplied operator has index 1. So we divide it we have this equation 1 minus rho in the times index is 1. So when we divide, we get exactly this expression, the same as in the analytical case. So that's an application of the index theorem in this case. Yes, thank you.
Thank you so much. Okay, any further questions? Tomek, are you happy or still do you want to continue your examination?
I have 2 questions. So my first question is about your integral from the beginning of your talk.
Yeah.
Okay, this Riemann-like sum related to this partition of unity. Can this integral be made in the spirit of the measure theory to have a measure with, let's say, kind of Tolkien coefficients?
Oh, I didn't understand because can you say it some?
Okay, so the values of your integral are in some version of Kantian algebra. The multiplier is divided by this essential idea.
Yes.
Okay? So this is an analog of Kantian algebra. Okay? And then my question is, since you are defining everything in terms of the Riemann-like sum,
Yes.
can this Riemann-like integral can be made a Lebesgue kind of integral with respect to some measure theory with coefficients in this Kantian algebra?
Well, the only thing I can say that I know the definition for compact space. I know the definition of this this integral, which doesn't have any integration and in it any Riemann sums or whatever. It's pretty simple, but I don't think I believe it's just kind of very trivial thing which I didn't think much about. Maybe you can do it with Lebesgue. You see, the whole thing should be a little bit local in a sense, but I'm not quite sure how you can do it with Lebesgue, but maybe you can. But it's as I say, it can be done even without integration. Well, or with integration which is hidden in some way. You just take some subalgebra which is generated by all this f of x, the function, and then the other thing is well, essentially it's like b tens c of x can be mapped into b tensor c of x can be mapped into b just because c of x is commutative. It's just, I don't know. It's for me it's a rather trivial thing. I don't know.
Okay, so the answer is yes.
It might be.
It could be made an integral in the usual sense in a very simple manner. Okay. So the second question is about your map from C0 So maybe it's second page or maybe third page. If you could come back,
Let me see.
maybe third one.
It's quite complicated. It's quite maybe quite long. Let's see. Yes, this one or
No.
next one?
No, next one maybe.
Next one?
Yeah. Next one. Sorry. You are counting down. Okay. Next one.
Next one.
Next one. Not yet. So please forward. One page more. I cannot see this. Yes. Maybe something like this. Yes. This map from C0, from this single algebra effects to operators on the tangent bundle. You are using double dualization. You are playing with dualization using this metric, invariant metric.
Yeah.
But if you don't use this metric, would you don't we have a canonical map? Because if you have tangent bundle, if you replace the tangent bundle by the cotangent bundle, you can restrict to the directions which are tangent to the orbits. Okay.
Yes.
So you have a clear economical map from C0, and then you have this tangent, this vertical, this tangent to the orbit space to CT of T star X. Don't you have something canonical independent of the choice of the metric? Or when you replace the tangent bundle and the cotangent bundle?
Yeah, but on the next page you see that there is a possibility to use the C-star algebra thing and map the C-star of the C-star of GX and to C-star of TX tau X using just I mean it's you use only abelian structure of GX and use abelian structure of tau X, or you use just measures. You use measures on GX and map measures into tau X. It's pretty canonical. I don't see any problem with this.
Yes, on this level there. So this means that you can dualize in two ways. Dualize first the tangent bundle and then these tangents to orbit spaces. Dualizing with respect to this matrix. And you can dualize it in the terms of the Fourier transform.
Yes, well, you are right, but the Fourier transform certainly is unavoidable. You cannot skip it somehow. It's absolutely necessary. But you can start with co-symbols if you want. So you can start with co-symbols as multipliers of this C-star of tau X, C-star of TX of X. So the co-symbols are already Fourier something which are these are objects which you can use directly to construct operators, and in the same way they don't depend on much on the metric.
Okay, so I wanted to be sure about this. Okay, thank you very much.
All right, any questions from Zoom? Alan?
No, I don't have any question. Thank you.
Any other volunteers? Well, if not, let us thank Gennady again. Thank you so much.
Thank you.
And I'll stop recording.